Lab 2 by Justin Siegel. This lab was designed to test the motion of a falling object that is dropped from rest and falls somewhat slowly straight down in the negative y direction. The object I chose was a tennis ball, as it is light enough to be affected by external forces, as in this case, drag, a force that acts opposite to the relative motion of the object with respect to a surrounding fluid, or in our case, air. Using the data I collected, two computational models were created based on Newton's second law, or the momentum principle, which include the velocity update, velocity final equals velocity initial, plus the net force divided by the mass times the change in time, and the position update formula, position final equals position initial, plus velocity average, or velocity final in this case, times the change in time. Then I created the first computational model, which just included gravity. So the net force is just the weight, which is mass times gravity negative times j hat. And the second one included gravity and drag. So the F net equals the weight plus the force of drag, weight staying the same, but the force of drag being b, a constant, times the magnitude of the ball's velocity squared times j hat. Here is the raw footage of me dropping the tennis ball from higher than 7 feet. I then put my video into Tracker so it could detect the motion of the tennis ball. I first input the diameter of the tennis ball, 0.066 meters. Then I aligned the axes so that the point 0, was at the center of the ball at rest, and that the ball fell directly down on the negative y-axis. I started at frame 47 and tracked the center of the ball for each frame until frame 68 when it hit the ground. Due to my inability to drop the ball directly downward, the motion of the ball in the X and Y were recorded, but we are only going to focus on the Y component for this lab. Next, I opened up GlowScript so that I could predict what the motion of the ball should look like with and without drag. First, I had to input the correct mass of the ball and change the initial Y position to the one I found in Tracker. The time started at 0, and I changed delta t to 0.0334, as that was the time between each frame in Tracker. B is 0, as we are not accounting for drag in this model. I then had to input the equation for weight, or Fnet in this case, as well as change the velocity and position update formulas. Finally, I changed the arrow scale for gravity so it would reflect how the correct length for the vector. I ran the program, which generated the model, a position versus time graph, and a velocity versus time graph. As you can see, the gravity vector points downward, velocity increases over time, and the acceleration stays constant. I then created my second computational model in GlowScript, this time accounting for gravity and drag force. The code stays the same until we find B. In order to find B, I had to check and guess until the final position on this code was the same as the final position on Tracker. I then inputted the formulas for Fnet, which includes the sum of the weight and the force of the drag, which I stated earlier, whose magnitude is proportional to the square of the object's speed, or turbulent drag, as you can see in the code here. I then updated the velocity and position update formulas. Finally, I updated the arrow scales for both gravity and drag so that the gravity arrow is in the direction of the ball's motion and the drag arrow is opposite of it. After running the code, a computational model, position versus time graph, and velocity versus time graph are created. As you can see, the drag vector is shorter than the gravity vector, which means there's an external force acting on the object. But this graph was really trying to show terminal velocity, or when the force of drag equals the force of the gravity, so net force is 0. This also means the ball did not fall at a constant velocity as seen by the next graph, but it slowly starts to become constant as time goes on. Since velocity isn't perfectly constant due to my air, there is acceleration, but the acceleration decreases as time goes on because the drag force increases. If the ball was initially thrown downward instead of starting at rest, terminal velocity would not change. Only the instantaneous velocity would increase. But because velocity does not affect force, so overall, the position versus time graph would start to become constant as time went on. Here is my final position of gravity and drag, and observed position versus time graph. The red line represents exactly what the ball should have done if everything was perfect, but obviously it wasn't, due to my error, as there was some movement in the X direction. What was observed was very similar to what should have happened, which makes sense overall, as the velocity was a bit quicker in the beginning, but ended out in almost the exact same place at the end. If we didn't include drag, as seen by the blue line, the velocity would be a lot faster, so it would hit the ground sooner than the other two lines. Thank you so much for spending your time listening to my lab.